morning. This is lecture number 35. We are still with module 6, matrix analysis of plane and space frames. If you recall, in the last class we had covered the conventional stiffness method. So in this session we will look at the reduced stiffness method as applied to plane frame elements, and this is covered in the chapter on plane and space frames in the book on advanced structural analysis. So I keep showing you these maps because I want you to see how the system of analysis is the same. The structure is changing but the methodology is not changing. We saw how well it worked for the simplest type of axial element, then we worked with plane trusses, then we worked with space trusses, then we worked with beams, and then with grids, and now with plane frames, and in the next class or the class after that with space frames. So we are covering all kinds of skeletal structures, and you can clearly see there are two broad methods. There is the stiffness method, which is preferred for programming compared to the flexibility method. In the stiffness method itself, you have the conventional stiffness method, you have a simplified formulation called the reduced element stiffness method, and that is a method that we are going to discuss in this session. If you recall, this is the 6 degree of freedom plane frame element that we used for the conventional stiffness method. This is a large matrix and it is a singular matrix. What is the rank of this matrix? 3. And one way of understanding why the rank is 3 is because you have, mathematically you have 3 dependent rows or columns, but physically what does it mean? Physically, for a stiffness matrix to be non-singular, you have to make the element stable. Now a singular stiffness matrix still works in a global scenario because your structure is stable. When you assemble the structure stiffness matrix, the KAA is non-singular, but here you can begin with a non-singular element stiffness matrix by giving how many restraints? 3, then only you have stability, and you can choose your type of restraint. We have been assuming that the simply supported condition is convenient and we will stick to that. So we are now going to use a 3 degree of freedom system, and it is very easy to write down. At this stage you should find it very easy to write down the element stiffness matrix. You can do it from first principles. You can also do it from the 6 by 6 element stiffness matrix. How? Just knock off the irrelevant rows and columns. There are 3 dependent rows and columns, and if you make it simply supported, you will find that the first row is important, the second is not, because we do not want the shear degree. So just delete the shear degrees of freedom, and you do not need 2 axial degrees of freedom. So that is how this reduces to this element. It is very easy to derive, very easy to remember. EA by L axial stiffness, 4 EI by L, 2 EI by L, 2 EI by L, 4 EI by L. Is it clear? It is actually a combination of your axial element and your beam element, right. You can also derive from first principles. You apply a unit displacement one at a time, and you can generate these diagrams must be very familiar to you now. It is not difficult. You can generate the element stiffness matrix. Okay. Now we also need the displacement, the TD matrix, that is the displacement transformation matrix. Well, we are familiar with this slide because we use this when we dealt with plane trusses. Okay. The plane frame is an advancement on the plane truss, because in a plane truss you have 4 degrees of freedom in the conventional system. So we are familiar with this transformation, minus cos theta minus sin theta cos theta sin theta, and you will recall there are two ways of deriving this. This is the kinematic way, but there is also an easy static way where you get the TD transpose matrix. So you are familiar with this. You are also familiar with what you do for a continuous beam, and if you have chord rotations, relative supports, settlements, then you have to use this chord rotation which is given by 1 by L, and clockwise chord rotations are treated as negative, but the equivalent beam and flexural rotations which is 1 by L will turn out to be positive. So you are familiar with these two. If you put them together, then you get what you need to do for a plane frame element with 3 degrees of freedom. You can easily work this out from first principles. What you need to recognize is, if you have any of those translations, you have to find out what is the elongation you get in the element. Right, so it is either cos theta or sin theta. If you get an extension, give a positive sign. If you get a contraction, give a negative sign. It is very easy. So you can generate this by pushing one at a time. I have shown here the translation effects. The rotational effect is very straightforward because there is no transformation required when you have a rotation, because it is the same, you get one. So let us just look at this. Let us look at the first one. This first column in your TD matrix corresponds to D1 equal to 1 in your structure. So if you have D1 equal to 1, you need to look at this picture. If you apply D1 equal to 1, that element undergoes a contraction of cos theta. So it has got a minus sign, that is why we wrote minus Ci. C stands for cos theta. At the same time, you get a chord rotation. Have you noticed? You get a chord rotation. The chord rotation is anti-clockwise. The value of the chord rotation is 1 by, not 1, it is sin theta by L, right? And so you get equivalent flexural rotations which will be clockwise, and that is why you get minus Si by L, minus Si by L at both ends. Is it clear? Any doubts on this? From first principles you can generate this. Alternatively, you can use a force approach and generate this and find the TD transpose. Did you understand what we did, the first column? Yes? This corresponds to the first degree, the axial degree. These two correspond to the rotational degrees. So if you have a chord rotation, 1 sin theta by L, clockwise you will get equivalent flexural rotations minus S by L. Is it clear? Like this you can work out for the second degree of freedom. If you take the third degree of freedom, it is a rotation, D3 equal to 1. That does not need any transformation here. So corresponding to D2 star you get 1, so 0 1 0. Does it make sense? That is all. Once you have got the physics in this, you have got it. This is actually not difficult to do once you realize that it is just a superposition of the plane truss element and the beam element. We did the same thing. In the beam element we had 1 by L because you did not have sin theta cos theta, but now your plane frame element can be oriented in any direction and not necessarily aligned with the global x axis. Is it clear? Okay, so if you have got this, then we can go ahead. This slide should also be familiar to you. These are the shortcuts you will take when you want to avoid considering axial deformations. Remember, you can convert you have to find out the sway degrees of freedom, the minimum sway degrees of freedom, and convert them to chord rotations, right. We had done this when we did the slope deflection method, remember. So we will invoke this concept when we want to do a simplified analysis. Okay. This slide is familiar to you. This is the standard transformations we do in the reduced element stiffness method, and this stepwise procedure for programming is also clear to you. Now we will take up the same problems we did by conventional stiffness method, and you can see there is a tremendous reduction in effort when you do the same problem by the reduced element stiffness method. Okay, so we will take this frame and we will solve it in two ways. One, we will include axial deformations. That means we should get exactly the same answers we got by the conventional stiffness method. We will also ignore axial deformations, and that reduces the problem even further, which is good enough for most practical cases, in which case the solution you will get will be what you would get if you were to solve by the slope deflection method or the moment distribution method. And let us see what is the order of error that you get if you ignore axial deformations. So you have that facility to either include or exclude, which you did not have in the slope deflection method. Is it clear? Let us go ahead. First you need to do the coordinate transformations. We try to partition TDA and TDR. You have to find the equivalent joint loads if you have a distributed load. In this case you have a concentrated load acting in between that beam. So you have to do this manually for reasons we have discussed earlier. You can't do the TD transpose and get this, which you could do in the conventional stiffness method because you had that many extra degrees of freedom. Then you generate the element and structure stiffness matrices. Mind you, the matrix you get here, the final K matrix, is exactly that which you get in the conventional stiffness method, but you are working with smaller initial matrices. There is one more thing that I think is worth noting. You need not find reactions if you are, anyway it is a manual method, so you can avoid FR if you want to and draw the free body and figure out the FR yourself from equilibrium. So that option is there in this method. So if you want, you can find the support reactions along with the unknown displacements, and you need to find the membrane forces. This last equation is similar to your slope deflection equation, except that you are now including the contribution, if any, of axial deformations, right. Okay. So first we will do the coordinate transformations. In this portal frame we will use 6 degrees of freedom for the same 6 active degrees of freedom which we did earlier, and 6 restrained degrees of freedom. The loading input is the same, F1 is 50 kilonewton and D11 is minus 0.10 kilonewton. Remember we did the same frame with and without an internal hinge. We will also do the internal hinge in this case and show you that you can solve the problem here. Now you are dealing with 3 elements, and each of those elements has 3 degrees of freedom. 1 star corresponds to the axial degree, 2 star corresponds to rotation at the start node, 3 star rotation at the end node. Okay. And you can choose your start and end as you wish. In this case you can see that for elements 1 and 3 I have chosen the start node at the bottom. Okay. You have to generate this matrix, give it a shot. What is the size of those matrices? For each element, what is the size of the TD matrix? 3 by 12, 3 by 12, right. Okay, let us do it together. We will demonstrate for 1 or 2 rows so that you get the hang of it. Okay, it is 3 by 12 and you can partition it where you separate the active degrees of freedom from the restrained degrees of freedom. Let us go through it, let us do a few of them. Let us take the first one. If you apply D1 equal to 1 in the structure but do not allow any other rotation to take place, what do you think will happen? Well, clearly this element 2 will undergo a contraction, so you should put this is minus 1, right. Nothing happens to element 3 and there is no bending in element 2. So straight away you know that this is minus 1, this is 0, this is 0, 0, 0, 0, got it. Now what about element 1? Element 1 is going to undergo a clockwise chord rotation but no change in elongation or extension. So clockwise chord rotation, anti-clockwise n rotation, so it's the rotation is 1 by 4, got it? So it's plus 1 by 4 plus 1, very easy to do because you are lucky you have a reticulated frame where the angle is 90 degrees. If it's not, put cos theta sin theta the way we discussed. Okay. By the way, in the book examples are given with a lot of inclined cases, you can go through it, but we will also do one inclined sloping legs problem. Take d2 equal to 1, very easy. If you lift up d2 equal to 1, only element 1 will be affected, will get in. So can you work this out yourself, or should we go through all the columns? What do you say? No, you are IIT student, you are bright guys, except that you have to go back and do your groundwork. See, we are only looking at concepts now, we are not going to sit and solve every second digit, but you have got a method, it is very clear. You have got assignment problems where you really need to sit and solve. So my suggestion is go through it carefully and do it. There is one more suggestion I can give you. If you want to minimize your work manually, you can throw away half that matrix, you can throw away all the restraint coordinates, because you can get those reactions from the member end forces anyway, right. So then your size becomes much easier, and it is full of zeros, so you just have to fill. In fact, when you program it, it's got null, it's a null matrix, then you fill it only where you need to fill it. So it's very easy to actually program it. Okay, so you know how to get the TD matrix for a plane frame. Fixed end forces, we have done this before. Okay, so these are your local coordinates. The elements 1 and 3 do not have any loads in between, so it is 0 kilonewton, 0 kilonewton meter, 0 kilonewton meter. Remember, 1 star corresponds to an axial force, 2 star and 3 star correspond to the end moments. There is no fixed end force for the first and third element, it is only for the second you have, and you have to be careful with that. We have done this calculation in the conventional stiffness method, so I will not repeat it, but it is important to work out those vertical reactions. In the conventional stiffness method, those vertical reactions went into your fixed end force vector because you had some coordinates there, you had 6 degrees of freedom. Here you have only 3 degrees of freedom, but you still need to work out the vertical reactions. Why? Why do you need the vertical reactions?
Those will be 1 star and 1 star in the first and third.
No.
The global coordinates thing.
They won't be 1 star because each independent is treated separately till you put it all together in the structure. So that answer is wrong. You are finding fixed end forces for each element, treating it independently. You do not pass on what happens in the second element to the first element, but you do it in the overall structure. So you need that information to find the equivalent joint loads. So even though you are taking shortcuts in reducing the number of degrees of freedom element wise, you got to see the big picture and put it all back at the right place. So as far as your element load vector is concerned, you have only this, there is no axial force in element 2, so 0 kilonewton. The left end fixed end moment is anti-clockwise 88.89 kilonewton meter, so it is plus 88.89, and the one at the right end is clockwise 44.44 and therefore minus 44.44. Is it clear? So it needs clarity in understanding to assign these correctly, otherwise you won't get the answer. Okay, got it? Now what do we do? Now we take this element alone has non-zero fixed end force vectors, and when you want to put it onto that structure, you have to do it by inspection. This is a shortcut method. Reduce element stiffness method, you can't do TD transpose and get it. So doesn't it make sense to write down your fixed end force vector like this, because what are the contributions from the 3 elements? The first and third elements have no contribution, right? Now this, look at this 88.89 matches with this force, right, F3F, and this 44.44 matches with 6. So 3 and 6 get those numbers, but then you have a degree of freedom here 2 going up and 5 going up, that is where you put 74.04. Is it clear? And it's positive, both are positive. Is it clear? That is why you need to calculate those friction forces, because once you look at the global coordinates, you are just looking, do I get any contributions from the elements? If I do, put them all together. Does it make sense? It makes absolute sense, totally rational logical method. Only thing, this needs a little input from your side. It is not mechanical the way the conventional stiffness method is. Conventional stiffness method, you can program it and just forget about it, do not even look at the physics of the problem. Here you have to, but that is what makes it interesting. This is good for human beings to do it with, that is good for machines. Okay. So as far as the support reactions are concerned, there is nothing, because elements 1 and 3 are where you have fixity, you have null vector there. This is done by inspection. So you have got FFA, you got FFR, and you got it by looking at each element separately. Clear? Can we proceed? Is this clear to you? Okay. What is the next step? No, we still need resultant loads, which is actually the same as this, because you don't, you have a 50 kilonewton acting at the third coordinate. So you do this, then you draw a sketch and you say, now this is a structure that I am going to analyze and superpose this result with the friction force values that I get. This structure is loaded with equivalent joint loads, and this is identical to my original structure. I have got rid of the concentrated load acting in the middle of the element 2, I have replaced it with equivalent end forces, both vertical forces and moment. Got it? And what is guaranteed? What is guaranteed is the dA vector will be the same, and that is the beauty of the equivalence, right? Okay. And also note, in this problem you have a 10 mm settlement. Now I have given you an assignment, the next assignment, where you get 2 problems only to do. One is a simple problem for conventional stiffness method, but I have thrown in a bit of temperature because we discussed that in the last class. Second is a funny shaped frame, a frame shaped like that, fixed here, hinged here, so you should take advantage of that hinge, and with a support settlement and a UDL on that beam. Okay. So this is kind of suspended from above and this is resting on the ground below. It is an interesting problem, try it. Okay. Element stiffness matrices, you know the formula, you know the EI by L, so this is child's play, you can do this. EA by L is also known. So for the first and third elements it is going to be identical because they are identical columns. Only for the second element it is easy to write. Always EA by L 0 0 and the rest is 4 EI by L 2 EI by L, very easy to write on. Okay, mechanically you can do this. What do you do next? You generate the structure stiffness matrix. You do it in 2 phases. First you do this KI TDI for the 3 elements. All this can be done by matrix multiplication. If you are doing manually also, it is not difficult, it is only a 3 by 3, 3 by 6. Then you add up all the contributions. You do not have to worry about slotting here because you got the TD, and you can generate, it is a big matrix, you get 12 by 12, and lo and behold this is identical to what we got by the conventional stiffness method, but the operations involved much less effort because you dealt with much smaller matrices. You did not have to worry about the slotting also. So it is a much more powerful method, and it is including the effect of axial deformations, and you are getting exactly the same results. So the next step should give you also the same result. You will get the same deflections and you will get the same rotations, so you can do that, and we got the same solution as we got earlier. Support reactions also is identical. So these 2 steps are common to both reduced element stiffness method and the conventional stiffness method, and so you can check equilibrium, find out your reactions, make sure everything is okay, find out your member forces. Now this is where there is a slight difference from the previous method. What is the difference? You have only 3 degrees of freedom. In the conventional stiffness method you got everything, you got the member end moments, member end axial forces, member end shear forces. Now you got only 3, the rest you got to figure out yourself, which is okay, So the member end shear forces are not directly obtainable as in conventional stiffness method, but can be easily computed from the free bodies applying equilibrium equation. So let us see how to do that. So this is what you get from those vectors. You have got the 2 end moments for each of the elements and you have got the axial forces. If it is plus it means it is tension, if it is minus it means it is compression. Now the rest of it you can get from equilibrium, isn't it? You take the second element, you can get the vertical shear force. So you do that, that is just one step away, that is it, you are ready. Bending moment diagram is the same, exactly what we got earlier. Now is the interesting step. Why should we work so hard with even that matrix? What is the advantage of ignoring axial deformations? The plane frame element reduces to a beam element. So you can work with beam elements, throw away the axial deformation. And one way to check the answer is put EA tending to infinity in the problem, because then it becomes actually rigid and you should get the same result, okay. But your effort required is much less in this method. So if axial deformations are ignored, the kinematic indeterminacy itself reduces from 6 to 3, that is a big reduction. Why does it reduce from 6 to 3? Because the columns AB and CD will not change in length. So you got rid of 2 vertical degrees of freedom at B and C, and BC also will not change in length. So you have only one sway degree of freedom, you can choose either the left end or the right end, the choice is yours, the deflection will be the same. This is what we did in slope deflection method and moment distribution method, right. So it is a massive reduction of effort, and let us not waste time in calculating reactions through this technique. So we do not even put global coordinates for reactions. So from a 12 degree of freedom model you are now a 3 degree of freedom model at the structure level. So it is a tremendous saving in effort, okay. So the 2 degree of freedom beam elements can be used in place of 3 degree of freedom frame elements. So we throw away the axial degree of freedom, that is it. So you have 1 star, 2 star for each of the 3 elements, and the restraint coordinates are not shown as they cannot be included in the simplified analysis. The reason is, once you are going for chord rotation way of dealing with sway, then do not bring in those restraint degrees of freedom, which means now how do you deal with the 10 mm support settlement at D? You understand? Now how did you do it in slope deflection method? Let us say that portal frame D goes down by 10 mm. Earlier you could handle it because in the dr vector you could fit it in. Now what do? In the fixed end force you have to handle it, because if D goes down by 10 mm, C also will go down exactly by 10 mm if CD is not going to change in length. BC will undergo chord rotation, and that you can get the fixed end moments from. So that is a clever way of doing it, and that is what we will do. But first, can you write down the TDA matrix? Do not worry about TDR, there is no TDR here. Can you write down the TDA matrix for the 3 elements? What is the size of each of them? What is the size of each of them?
2 by 3.
2 by 3, right? 2 by 3. So write them down. This you should do. No excuse, this is simple. Write down the 2 by 3 TDA matrices for the 3 elements. Will it be identical for elements 1 and 3? They have the same,
Yes,
they are going to behave identically, is it not?
Yes, sir.
The start node is the same at the bottom. So reduces your effort considerably. Write them down and tell me the values. Okay, let's take the second element. What's it going to look like? What's a TDA matrix for second element? Very easy. What's it going to look like? 0.
0.
There is no -1. Anti-clockwise is positive. 0 1 0 0 0 1, right? And for the first and third elements, 1 by 4 0 0 1 by 4 1 0. Is this clear to all of you?
Not identical.
They are not identical. Oh yeah, that 0 1 is shifted. Yeah, you are right. Only the chord rotation is identical. The rotational degree of freedom 3, the global level, pushes that 1 to that corner. Is it clear? Very easy to do. Any doubts? Can we proceed? This is a massive simplification. Remember where we started? We had that 12 by 12 and then I had to explain each column and each. Now this is child's play, right? The tremendous reduction in effort, and so procedure is the same with much less effort, but considerations are limited to active degrees of freedom, so you can chop off some of these calculations. First thing, knock off the TDR, we do not need TDR. Then just need KAA. What is the size of KAA? 3 by 3, that is all. This is nanotechnology, working with small matrices, and you are still getting good results for actual practice. Okay, what about the support reactions? Who cares? Throw it off. Okay, so you just need dA, that also dA minimal, 3 degrees of freedom, plug it in and get it. So this is what we are going to do. So you have to take care of that 10 mm support settlement in the manner that we did in slope deflection method. So I hope you are familiar with this calculation. You have this additional fixed end moment caused by the support settlement. That element will just go down. Okay, there is no force in that element. Okay, so you work this out. You can find the total fixed end moment. Shall I go ahead, because we have done this problem earlier? So the first element and third element will have no fixed end moments because they are vertical columns. The second element will have fixed end moments caused by 2 loads. One is a direct loading 100 kilonewton, the other is the indirect loading 10 mm settlement in the right. That means clockwise chord rotation of 10 divided by 6000. Okay, so this can be done. You have got the fixed end force vector. What do you do next? You get the resultant load vectors in the same manner. Okay, and here you do not worry about those concentrated loads as we did earlier, because they are not going to affect the displacements because they are actually rigid. So even if I put them, it is not going to make any difference. It is not going to cause any actual difference. Is it clear? So I do not even need to do that exercise, and so this is identical to slope deflection method, but you made an assumption. Assumption is actual deformations are negligible. How true that is for this problem we will know shortly. So you have got these moments. So your problem is now reduced to this problem: 3 loads, no vertical loads. Element stiffness matrix is very easy. What's it? 4 EI by L, 4 EI by L, 2 EI by L, 2 EI by L. So that's easy, you can do it. Or you go back to your previous 3 by 3 and knock off that EA by L row and column. First row you will get this. So no big deal. Structure stiffness matrix, same procedure, you generate. Will this structure stiffness matrix be the same as what you got earlier? Will it be the same? Yeah, first of all it won't be, because first of all the size is different. This is 3 by 3, that was 6 by 6. So we have this is nano, we are playing very small, and you have got these values. Are the units the same for all the components in the stiffness matrix? No, because you have translations, you have rotations. That is why I do not write any units outside, so do not do that. there are no common units here. Okay, how do you find the displacement? Same method, you get some answers, right? Now it's interesting to check whether these answers, these deflections are what you got when you considered axial deformation. So this is what we are getting now, and it's pretty good. This is the exact solution. 13.37 mm is what you get when you ignore axial deformations, and it's the same left end and right end because we are assuming that beam will just move like a rigid body. But the exact answer is 13.39 mm and 13.33 mm. Is it okay as an engineer? Civil engineers make errors in the order of meters, so compared to that, 0.03 mm error is nothing. Not only that, in practice you must take all these solutions you get from the computer with a big pinch of salt. The reason is so many unknown parameters are there. Okay. First of all, you have written a load of 50 kilonewton. Where did you get it from? From the wind? Sorry, wind is very uncertain, right? So there are so many uncertainties involved. You have to have a probabilistic look at the whole picture. You should also know what's the kind of material that you are using and what is who is going to build the structure. But that's no excuse for an analyst. An analyst should say, you give me whatever you give me, I will give you to the level of accuracy that you get, and I should know what is the percentage error involved. So analysis is one thing, design is another. For design you have to be very practical, but we as civil engineers, while we do structural analysis, so we are quite happy with in fact we know that 13.37 could in reality be actually 15 mm. It's okay. It's okay. Did I tell you that joke about 2 plus 2? No? Okay then. What is 2 plus 2? The answer depends on who you are. If you are a mathematician, what do you think 2 plus? What's the answer a mathematician will give? If you are a bad mathematician, as you are, you will say 4. But if you are a good mathematician, a professor of mathematics, you will never give anything that is of practical value to anybody. So you will quote a theorem saying that if there are two real numbers, they are adding up, and you give the lemma which says it can be, and you can plug in your numbers if you are interested, because you are interested in the algebra. Okay, so that's the mathematician. If you ask a good civil engineer, what is 2 plus 2, what do you think he'll say? Good civil engineer.
4 plus 1.
Huh?
4 plus or minus 2.
4 plus or minus 2. Then you are a bad civil engineer. But at least you didn't say 4, but you depends on what kind of errors you are willing to tolerate. So I would say most good engineers would say something, say between 3.5 and 4.5. I mean, that's not as bad as 2 and 6. 3.5 and 4.5, why do you say that? Because you know jolly well that you will never get 2 plus 2 to begin with. That 2 itself will have uncertainty, right? But the joke is not on the civil engineer, the joke is on lawyers and chartered accountants. If you ask this question to a lawyer or a chartered accountant, what do you think will be the answer? They will say, what do you want it to be? And if you say you want it to be minus 325.6, they said, so be it, but my consultancy fee will be this much, and you will hire the mathematics professor and the civil engineer to prove to you that 2 plus 2 is minus 325. So be a good civil engineer and appreciate the enormity of the errors that are made. Membrane forces, you get these. Mind you, are getting only the moments, and what do you do with those moments? You have to generate the axial and shear forces, which you can from the free bodies. You will get some difference from what you got earlier, surely you will, right? But you are really, and you can work out the the shear forces and actual forces from equilibrium. Okay, first you get the shear forces, then you get the actual forces. Then you draw the bending moment diagram. Now this is interesting. Who cares about deflection? I want to design my structure for bending. How do these bending moments compare? And you'll find that this is pretty good. 69.845 is what you got without actual deformation. 69.744. As long as it's between 60 and 75, it's okay. Well, you will design it for 70. That's what you do. You design for 70, and on top of that, there will be a factor of safety increase. Okay. Next topic: how do you deal with moment releases? Okay. When axial deformations are ignored, plane frame element reduces to a beam element. So we can take advantage of moment release at a hinged end or support or internal hinge. We do what we did for the beam. That means you ignore the degree of freedom associated with it, modify the element stiffness. 4 EI by L becomes 3 EI by L, and you have only 1 degree of freedom. If the other end is hinged, if it's a guided fix, you know it's going to be EI by L. So we will do this. This is what we've done earlier. Let's demonstrate. Let's demonstrate for that same portal frame with an internal hinge. This is something we could not do in the slope deflection method, right? We couldn't do such problem, but now you can in a matrix formulation. Is it clear? I have taken the same frame. We are going to ignore axial deformations. Okay, make our life simple, but we've got a hinge there. Is it going to make our life more complicated, or is it going to make it easier, that hinge? It should make it easier. Okay, so let's make it easy. Solution procedure same, coordinate transformations. Okay, now look, the changes we are making now compared to the previous problem is, in elements 2 and 3 we knock off the rotational degree of freedom at C. So your size of your stiffness matrix, your TD matrix reduces. You have 2 degrees of freedom for element 1, no change there, and you have only 1 degree of freedom for elements 2 and 3, and you should release at the right place where there is the moment release, there is the hinge, internal hinge at C. It matters little whether the hinge is internal or at a support. Clear? Okay. How will this change? This is the change. Okay. Another thing, in your global coordinate 3 is gone now, because you can't talk of D3 in your structure because you have 2 different rotations in the connecting members. So you remove it, you don't need to put a clamp here. Okay, just remove it silently. So you have only 2 degrees of freedom. Your degree of kinematic indeterminacy is only 2 in this problem. Remember when we did by conventional stiffness method, we had 5 with the hinge. Without the hinge it was 6. Here without the hinge it was 3, with the hinge it is 2. So you have D1 and D2 in your structure as your unknown rotations. Is this clear to you? The TD matrix? It just follows from the previous case. Okay, just ignore that rotational degree of freedom at C. Then fixed end forces, what's the change we need to do compared to the previous one? You have to release at C the moment. So you are dealing with a propped cantilever. You know how to find out? You know how to find out, right? For that concentrated load, you know what to do. You have to take half, carry over half, and for the support settlement, it's not 6 EI by L squared, it's 3 EI by L squared. Is it clear? You know that for a cantilever. That's what you do, and you get the answers. You get the fixed end forces. The size of your matrix has now come down from 3 to 2, your vector, and that's what you get. Your fixed end forces, your nodal forces, your equivalent joint loads are now, that 50 kilonewton was given to you as input. The only thing that came extra is that 158.572. So you are going to get the same response with this as you got earlier. Is it clear? You don't put any vertical forces, you don't put any moment at C. But here you might have a bigger effect of axial deformations. The reason is this frame is very flexible. So how much it moves will be affected a bit by axial deformation. So let us take a look at what you get. What about your stiffness matrices? For element 1 no change, you have the same 2 degree of freedom. For elements 2 and 3 the change is 3 EI by L, right. So you do that 3 EI by L, write down these values. It is a 1 by 1 matrix, very easy to calculate. Structure stiffness matrix you can generate, it is a 2 by 2 structure stiffness matrix, right, because you have only 2 degrees of freedom. Find the displacements. Now your deflections are 23.48 and the exact solution is also 23.48. Oh my, so this is very good, I mean this is excellent solution, excellent answer. I think the error you get is when the legs are inclined, in that I will show you there we get a little error. So very good answers. Also the vertical displacement is 10.07 compared to 10 at the bottom. Okay. So member end forces, calculate, these results also match with what you got earlier. Draw the free body diagrams. Bending moment diagram, final comparison, some minor error but certainly no major error. Is it clear? So with this we have covered reduced element stiffness method as applied to frames. Clear? Thank you.